Dr. Marc Weissburg is professor at Georgia Institute of Technology. He was my postdoc advisor many, many years ago, and is doing really incredible work. And so I wanted to share with the Earth and Space Science community some of the great things that he's doing. So I'm going to turn it over to Marc to introduce himself a little bit, tell us a little bit about his background as he gets started. So thank you very much for joining us, Dr. Weissburg, and we look forward to seeing this presentation. Thank you.
So presumably you should all see a screen now with a very muddy figure of me. If you don't see that, somebody sing out and we can deal with the technical difficulties. But this is sort of the sort of work that I was doing a lot of when Dr. Keller was working with us, and it is what I still sort of consider my, I don't know, I guess my bread and butter, or at least my first love, and that's understanding how particularly marine organisms communicate and use chemical cues, and how that affects their ecological interactions. And so I'm basically a marine community ecologist, as you might see there from the copious savanna mud that I'm adorned with. I am also, I have another hat, and that is as somebody who does biologically inspired design. And biologically inspired design, simply put, is understanding what natural systems and organisms can teach us about how to have a better technological approach to particular problems, right? And so, for instance, Velcro is an example of biologically inspired design that you may not know of. It was, in fact, created by somebody who was looking at plants and how they stick to animal fur, right? And so this idea of biologically inspired design is a, I guess I'll call it an area, certainly a new area of how to use biological systems to inform our own technology, right? And that's something that I've started to do fairly actively over the last few years. And I've done so in the context of an ecologist. I'm trying to use what ecological systems tell us to organize human infrastructure so that it's more sustainable, right? And so normally when we think about sustainability, we can think about something on the product scale, or rather something that is sort of embedded within the product, the materials that it's made of, how we get those materials. Those have large impacts on sustainability, right? Things that are scarce, that require a lot of environmental harm to extract, are bad. Things that are common, that can be recycled, are good. We can think about the amount of energy, right, that it takes to make a product and dispose of it, right? Some of you might be familiar with this idea of life cycle analysis or cradle to grave design, right? The amount of embedded energy in that product and the amount of energy that can be recovered when that product is done with its useful life, right? And so that's something that informs what we do when we make something, right? Or informs the thing, how to make a thing in the right way, right? Things with high embodied energy that we can't recover are not so good. But there's a much larger scale out here, and that is sort of the system scale, right? That comprises our entire manufacturing and transportation infrastructure, and the infrastructure that's used to support cities and other collections of humans, right? And we don't really have very good ways to sort of understand how to make those things sustainable, because systems are complicated, right? But it is the sum total of all these activities that affect our ability to live peacefully on the Earth along with all the other inhabitants, right? And we obviously are not treating these other inhabitants in a peaceful and graceful way at the moment, right? And that's, of course, a big part of our problem. So at some point it occurred to me that, in fact, there are strong parallels between cities and the natural systems that I study, right? Complex human systems, such as cities or collections of industry, or even an industry itself, are not like ecologies. They are ecologies, right? If we take away the fact that when we think of an ecology, we might think of an animal, eating another animal. The fact is that what a industrial system does, or a collection of industries do, is exactly the same thing functionally, that's the important word, as what happens in an ecosystem. And that is to say that in an ecosystem, right, as we all know, animals eat other organisms, right? They produce and transfer energy, right, by transferring material. This is exactly what a collection of industries do. They consume material, they consume energy, they transfer material to other industries, or transform them into components that are used by other industries. They produce energy that is not harvestable necessarily by other organisms. That is an ecology. That's a food web. And it turns out that we have good techniques for understanding energy and material transfer in food webs. What I've done over the past 6 or 7 or 8 years has been to delve into that theory and understand how we can apply that theory to collection of human infrastructure. Right? So a little ecological background, right? This is a food web. Most of you have sort of seen this diagram at some point in your life. Things are eaten by other things. That bunny rabbit down here is eaten by a variety of organisms, such as these owls and hawks and foxes. The grass is eaten by the grasshopper, which is eaten by the rodent, et cetera, et cetera, et cetera. So this is a pictorial description of what a food web is, with linkages that are shown by these arrows. And I've extracted one part of it here, right? We have 3 organisms, right? The grass is eaten by the grasshopper, which is eaten by the rodent. And so each one of these components is linked, and we can turn that into a matrix, right, that describes that interaction. And so this matrix here, with rows and columns as these 3 organisms, basically is a matrix description of those linkages. So in this particular column here, organism 1 is eaten by organism 2 is eaten by organism 3. Right? And we can extend this logic, right, this matrix approach, right, over a huge food web, right, as shown here. So now we've taken that entire food web and we've made this adjacency matrix, as it's so called. And so this is a mathematical description of the topological structure of that food web. And because it's a nice mathematical description of that, we can generate a whole number of useful quantities that describe how that food web actually works. And some of those quantities are listed below here. We'll see them again. I don't think the formulas are super important, but we have formulas that tell us how linked things are to one another, how many predators might consume an individual prey species, how many prey species an individual predator might consume, the ratio of consumers to producers, and what have you, right? So all of these numbers we can use to describe the topology of that matrix in a much more precise way than, let's say, the picture that you see here on the left. Right? There's another feature of this matrix that's particularly important, particularly when we think about things like energy use and energy cycling and energy efficiency. And that is that we can basically take this matrix through a series of calculations which are described here, which I will not go into, and get some indication from this structural matrix of the existence and the magnitude of cyclic pathways in a system. Right? Where a cyclic pathway is one which is able to move energy through the system without it being lost to the environment. Right? And so again, I won't go through the calculations, but I will tell you that the number that results, right, is an eigenvalue of this matrix, right, that describes the relative proliferation of flow pathways in a matrix. The higher that number is, the more pathways there are for energy to cycle, and the more potential there is for recycling in that network, rather than a sort of a straight through pass-through system where the energy comes in, some fraction is used, and the rest gets exported outside the system, right? And we all know ecological systems do that, right? They're very good at recycling energy, and we'll talk a whole lot about that in a second. Here, right, we have one cyclic pathway, right? Or 1 to 2 to 3, back to 1, right? The maximum eigenvalue of that matrix is 1. Here, we have actually more than one cycle, right? We have this cycle here, which and this cycle here. And so as we increase the number of cycles, that eigenvalue increases, right? So better is bigger, right? So, excuse me, this approach allows us, excuse me, to interrogate any system where energy and material moves through it and understand the topology of the system and understand the consequences of that topology for this process here, which is energy cycle, right? And so we can apply that to collections of human industry, right? And I'll start out by thinking about this idea of an eco-industrial park, because they have been held up as a way to organize human manufacturing in a way that is more cyclic, right? So they were sort of explicitly designed to bring in a bunch of companies together such that the production economy now becomes circular, right? By allowing companies to exchange basic inputs or outputs, to use waste energy or waste materials. All of this limits the material consumption and exports to the environment and results in increased efficiency and presumably reduces the environmental impacts and burdens, right? And so this is one of the ideas of industrial ecology, right? Where through this collection of industries, we transform what is a linear manufacturing cycle, energy in, a product out, waste into the landfill, into something that's more cyclic. Turns out, as you'll see later, that there's a fairly large disjunction between the reality and the implementation, right? And that's something that we wanted to think about, right? So this is a typical industrial park that we've now represented as a food web, right? Where again, the arrows are indicating who's being eaten and who's doing the eating, right? It has about 17 industries and about 24 links. 10 of those industries are what we would call producers, right? That give material to other industries. And 15 of those are consumers. They consume products or energy from another system. And again, a single individual can act as both a consumer and a producer, right? And so there are more producers plus consumers than there are actors because of the dual role. So this is exactly how we would depict a food web. This particular example is super famous, and it has been held up as sort of a model industrial park. There's 100 papers written on this one industrial ecosystem, right? All of which pointing out how great it is and how cyclic it is and how it very clearly embodies the idea of a circular economy, right? It's actually a bunch of hooey. This is the matrix, right? Just as we've done before, we can take the industries and express them as both predators and prey. And you see that here, where the linkages are given by ones and zeros, one having a link and zero having no link. Right? Now, it turns out that there are hundreds of examples of this. This is the most famous. And so one of the first things that we did early on was to try to figure out whether this idea that we have of a circular economy is working. And if so, how and why, and if not, how and why not. And we did so by comparing the features of this industrial systems that we see here with the features of real natural ecosystems, right? On the presumption that ecosystems are really good at this, and we can benchmark the performance of human systems in a very deep way by using the same methods of analysis that we would apply to an ecological system and comparing the human and the ecological systems and seeing how well the second one replicates the features and efficiencies of the first one. Right? And so that's this analysis, and let me step you through it. Each one of these graphs, the three that you see here, shows a particular feature, topological feature of an ecological system that we can extract from this matrix. And the rows or treatments, if you will, are different types of systems, ranging from the eco-industrial parks all the way through a variety of data sets that correspond to ecological systems. And the best comparison to make is between this EIP here, which is our human systems, and this column all the way over here on the right, which is the most sort of authoritative and complete set of data on natural systems that we can find. Right? And so what you can see is the sort of topology of the human systems here in no way recapitulate the topology of the natural systems. That is, human systems have very unequal ratios of producers to consumers. There are fewer consumers for a given producer in a human system. A consumer in a human system consumes a limited number of quote-unquote prey species. Right? And as a result, and that's what these three graphs show you right here, right? So low predator-prey ratios in human systems compared to the natural analogs, prey species that are eaten by very few numbers of consumers as opposed to an ecological system, predator species that eat a whole lot less different types of prey than natural systems, right? So the linkages in human systems are incredibly specialized, right? And a given entity in a human system is very unlikely to be linked extensively to other members of the quote-unquote web that it exists in, right? So it's really a rather sparse sort of web, right? And as a result, which you don't see here, is that the capacity for cycling is obviously going to be much less because there's a whole lot less interconnectivity in a way that counts, right? And a good way to sort of understand why this is true is by looking at two different human systems, one of which is actually reasonably close to the organization of a natural system, and that's this one right here, right? And this is the canonical system that everybody thinks is so great, right? And what you see in the, let's start over here, red boxes constitute key elements in these systems that are widely linked to other elements and that act sort of in a way that a detritivore or a decomposer would do in a natural system, and that is essentially taking waste energy or materials and transforming them into something usable for other industries and feeding it back into the system. Right? And so all those green arrows are the cyclic pathways that are produced by these two highly linked components, right? And you notice that even other components in the system are linked to often more than one thing, right? And there's only one of these things here which basically doesn't have much linkage at all. Right? Here is the very famous canonical system that doesn't work very well. And what you can see is that these quote unquote key elements, right, the sort of detritivores in the system are not highly linked. And there's really only one cycle in this system, right? And everything else is linked, but in a very non-cyclic way, right? There's no way to get from any of these components to any of the other components through those gray arrows, right? And so what this analysis teaches us, right, is that the way that we've organized our own human systems, despite the fact that we put a bunch of things together, in no way replicates even coarsely the way that natural systems are organized. And as such, the way that they operate is very dissimilar to the way that human systems operate as well. The role of these detritivores, right, which is this set of organisms here in a natural system, is highly underwhelming in human systems, right? So earthworms, right, we all know, right, if we're gardeners or even if we're just sort of normal human beings that are paying attention, right, that earthworms basically are these supercritical components in a lot of terrestrial ecosystems because they take dead organic material or waste organic material and they transform that into energy or materials that are then incorporated back into the system through a variety of other loops, right? Themselves, right, because things consume those earthworms, right? Those earthworms make nutrients available for plants and for other organisms that are also consumed, right? And so this is, you know, not surprisingly, an important element, but analysis shows you how important it really is in these human systems. And so what you see here is the number of sort of active detritivore links, right, in a human system, right, defined as something that's taking a waste product and making it re-available to the other components of the system versus the capacity for cycling or cyclicity in that system. And remember that one, right, is one cycle, right? And the median for humans, for natural systems, the median for natural systems is somewhere over here, right? And so, not surprisingly, right, as we make those detrital, quote unquote, actors more important in human systems, we strongly affect the capacity of those human systems to cycle energy. All right, so again, this is a really good example, right? This is another example. We have one key actor here, right, which then makes the waste materials and energy available to all these other actors, and that system is over here somewhere. Whereas this system, right, where we have a sure fit of that and they're poorly linked, is over here. Right? There's basically only one good cycle in this system, composed of multiple cycles in the system. So that's all very good, right? It shows us that we can characterize human systems in a way that is analogous to how we have characterized natural systems. We can extract information about how such human systems work, how poorly they work, specifically, and why, right? So we have a good descriptive systematic account that we can apply to lots of things that are important for humans to diagnose how well we're doing and or how poorly we're doing, right? And it's pretty simple, right? All of this is very simple data to obtain, right? Who eats who, particularly in an industrial system, right? And so that's great. We know what the problem is. Now the second question is, can we fix it? Can we use these methods, not in a descriptive sense, but in a prescriptive sense, to help us understand how to do things better? And that's what we'll talk about a little bit now. And the answer is yes. And I'll show you a number of ways in which we're doing this. Because we don't want to just describe things, we want to make them better. And so the first example that I'm going to show you is what happens in a carpet manufacturing network in Georgia. It's the Interface Carpeting Company. And if you don't know about Interface and are interested in sustainable manufacturing and design, or just are a fan of companies actually trying to do the right thing, Interface is a company that you should know about. They made a commitment probably about 15 years ago to be zero carbon. And they are pretty close to that. They also happen to be the world's largest carpet manufacturing company. So it's not a trivial thing that they've done. They recycle a lot of their carpets, and so they have a network of manufacturing systems and consumption, places where the carpet is consumed, right? That is industries and houses and things like that. Recycling or reuse facilities that take back those products and extract the usable components, and landfills where the refractory material goes. And these are distributed all over this region here in Georgia. And so they organize this in a certain way. Certain manufacturing centers are linked to certain consumer hubs, which are linked to certain recycling centers and landfills, right? In a way that an ecosystem would be linked, and these are all sort of spatially segregated. And the question is, can you organize this in a way that reduces the amount of energy used and the pollutant burden, and how do you do that, right? And it's essentially, well, we've got this recycling center here, and we need to connect it to this landfill over here, and this recycling center here is going to feed this landfill over here, and these carpet manufacturing centers buying these consumers, which are, bringing their waste to this particular recycling center, blah, 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 right? So it's a pretty complex problem, since there's a large number of these things, right? There are two ways to solve, but the way that we normally solve this problem is something called objective function optimization, right, or maximization. And that is that we have a series of differential equations, right, all of which are sort of mutually dependent on one another. And the goal of those equations is to reduce a particular cost, right? To reduce the cost of transport, to reduce the cost of materials, to reduce the cost of labor, to reduce the amount of pollution that's going into the atmosphere, et cetera, et cetera, et cetera. And so there's, I think, 16 or 18 such equations that describe this particular system from all those cost perspectives. And one optimizes the system by finding the absolute minimum for a particular cost, and then trying to optimize the overall system, and each one of those 16 components is then examined, and the disjunction between the optimized value and the value in a particular system is determined, right? And the goal is to reduce the deviations from each optimized component to how that component is operating in the context of the system. So it's a big, gnarly mess, and it depends on a lot of information. How much sulfur is being produced, how many miles you're driving, all these kinds of things, right? It's, and it's a simulation-based approach, and it's terribly cumbersome and not always guaranteed to find a minimum, right? The second way is to think about doing this from the bioinspired function component, and that is to describe some functions that replicate in as faithful a manner as possible the structural components of a real ecology, right? Vulnerability, generalizability, the things that I mentioned before, right? Of which there are few in number, and they're easy to figure out. And so we did the following. We compared the traditional approach, which had been done by others as well as us, and then optimized the system using only 5 ecological variables that correspond to what we know about the structure of a well-performing ecological system. And we did 40,000 simulations with 40,000 different combinations. And in each case, we looked at the objective function, and we looked at the bio-inspired function that's based on ecology. And you see the results here in this scatter plot. That's 40,000 simulations. The correlation on this scatter plot is about 0.995. Something that I would never see as an ecologist, right? If I got data like that, I'd be like, wow, that's amazing. And the engineers were like, we've seen better. I'm like, you guys are out of your minds. Okay? If you organize this carpet manufacturing system to correspond to 5 simple ecological variables, you automatically make that system the most cost-effective and the least burdensome to the environment, with a whole lot less information and a whole lot less effort. So we have a very nice prescriptive way to look at some very complicated systems. It turns out that there are other ways that we can use this ecological network analysis. And we can apply them not only to things like a carpet manufacturing network, right, which is this big sort of extended multi-entity system, right, but we can look at what happens within single manufacturing plants that have a whole variety of processes to them. Right? And so what you see here is a system that we worked on in China. This is a steel mill in China. And steel mills are really, in themselves, fairly complicated entities with a whole bunch of sub-processes, I'll call them, that exchange matter and energy, right? And so this is the sort of topology, right? This is a network diagram, an ecological network diagram of a steel mill, right? That shows all the different sort of bits that have to happen when one produces steel, and the network of connections, in this case with respect to water, because this is the problem that we worked on. Right? I want to direct your attention to the fact that this is a huge area, right? This is hundreds of acres, right? The rolling mill here is about a mile. That's over here, right? This is over a mile from end to end, right? And there's a whole bunch of green space here. Keep that in mind. So, what can ecological network analysis teach us about this, and how can we make this steel plant more energy efficient? Steel production is about 10% of the world's carbon footprint, and 70% of that is in China. So, all right, now if you've fallen asleep, this has probably woken you up, and you're now sweating because it's a nasty set of equations. I'm not going to go through it. Right? What I'm going to point out to you is that just like we can do a matrix of structural connections with ones and zeros, we can do a matrix where the elements are now the amount of flow that goes from one cell to the other. And so rather than having topological descriptions, we can have more nuanced descriptions of what's going on in the system. And the end result, the end result of this particular calculation, right, is something called Finn's cycling index, which is the fraction of energy or material in a system that is cycled, right? As opposed to going in and then leaving the system as an export. And so what we wanted to do was to sort of optimize this steel plant to make water efficiency key. And again, I'm going to contrast this with the traditional cost-based objective function technique that I told you earlier. This is the series of equations that would describe that, right? With all these particular variables that we know from our colleagues that understand how these steel plants work, right? And so each one of these flows with all of these components has a cost associated with it. And we'd like to minimize, right? The objective function technique is to minimize each one of these costs, right? And then to overall think of the system that minimizes the aggregate. Okay. We added to that the Finn's cycling index function and maximized the system, optimized the system based on both minimizing costs and maximizing the amount of water that is cycled through. Okay? And the math is over there on the right and the left if you want to look at it. I recommend just trusting me on this because it's a pain in the butt to go through. So we did a multi-criteria optimization and we found the following. You can minimize costs, right, which doesn't do anything at all to minimize water draws from the environment, right? Or said another way, minimizing costs does not automatically result in a more cyclic system, because what you're minimizing, right, are only these particular, right? You're minimizing this aggregate function, right? And so minimizing some parts of that necessarily mean minimizing this. We can, however, jointly optimize both cost and recycling. And there is almost no penalty for cost when we do that. right? So by adding the cycling calculations in here, we increase the cycling by almost a factor of, what, 5, right? With almost no penalty at all in terms of cost. And so the ecological flow perspective here allows us a very substantially different view of what's going on in the system than the kinds of ways that an engineer would maximize this system or optimize the system without this ecological perspective and knowledge, right? And so, man, my mouse is super sensitive. And so what's going on here, right? This is the fraction of the flow in the system from these various components. And the two components that are affected when we do the cost and cycling dual optimization are the amount of flow that comes from the desalination system in the steel mill, right? And the amount of flow that is basically coming from freshwater draws. And so we radically increase the former and we decrease the latter. And so again, there's not a trade-off here, as you might suppose, between minimizing the cost and maximizing the sustainability. Those two things go hand in hand in a very precise and quantifiable way. We don't have to wave our hands about this. So can we go further? Can we take this optimized system and then further reduce the environmental burden? And this is, again, where some of our ecological knowledge comes in. Again, when we looked at this system, what we realized is that there is, particularly with respect to this water network, a lack of a component that is really sort of acting in an ecological way to bring water back into the system. The desalination plant does some of this, but not a lot of it, because it's very limited in the sorts of water that it can treat. And so we used the idea of ecosystem services through a constructed wetland to think about how to make this flow more cyclic, right? And return water back into the natural processes. And the interesting thing about the constructed wetland, right, and this is the network diagram that you see here and the links that were added, is that a wetland is both a mass, right? It has embedded energy as well as a water recycling component to it. And we can use that embedded energy to also recycle it back into the steel mill. In other words, being very faithful to this idea of what a decomposer really does, right? Things eat earthworms, right? Earthworms recycle energy and matter back into the system. I'm sorry, right. So we did that, right? And what we found out was that you can use even less water than you used before. And you can use less energy because the biomass that is embedded in that natural system can be converted into char, which can then be used in place of coal. And a 1% energy savings doesn't seem like much, but extrapolated over the enormous amount of energy that's used in a steel plant, it's actually quite a lot, right? And even from an optimization standpoint, when you do these optimization things, oftentimes you're only changing things by a few %, right? So this is a pretty significant result in the context of these systems. And so again, is this idea that this sort of decomposer link, right, that allows for greater linkages and greater movement back into the system is super critical, right? And we've used essentially a natural system and used the ecosystem services in a natural component to supply that role. And so we looked a little bit more broadly at this. We had access to a whole number of systems that were designed or being designed by some collaborators with us. And we broke them up into systems that either sort of included a kind of a natural ecosystem service component, right? Those systems that have an agricultural or a natural environment system component to them versus other kinds of components like utilities. and asked, how well do these things cycle? And do they sort of correspond to the kind of way that we think that natural systems are organized? And you can see the results here, right? For natural systems that, or for systems that use these kinds of ecosystem services, they have a hugely greater capacity to cycle. Actually, let me explain this diagram again. These are various systems or places, right? An agricultural system, a natural environmental system, a utility system, with or without these natural components, right? And so again, the natural components tend to make these systems operate better, and they're more strongly linked to one another, right? So the urban industrial systems with these natural actors show enhanced cycling and more linkages between the components, right? And so now our question is, right, how can we design processes, right? Design a design process that allows for this to happen more often, right? I think I'll skip this. Let's do this very briefly. Let me point out that we can think about robustness as well. And that robustness is a systems property, and it tends to trade off with efficiency. So as systems become less efficient, right? This is a very efficient system, right? Things go from A to B to C. This is a less efficient system because we don't know where things are going to go. They become more robust, right? And in fact, it's the redundancy that allows the system to be robust, because if we take out the turtle link, we can still transfer energy from prawns to alligators. If we take out the large fish link here, nothing in the system from here goes to here, and the system falls apart, right? And there are ways to calculate this resilience property or robustness property using the ecological analysis that I've described to you. And you get these curves that look like this, where, and again, we won't worry about math. These are super efficient, highly constrained systems. These are very, very resilient, robust systems, but are inefficient. And you notice that natural systems sort of occur on this particular sweet spot here, right? And the suspicion is that natural systems that are either too efficient or not efficient enough go away, right? And so we're left with this sort of optimal combination right here. Right? And so we looked at that for a system in an auto manufacturing plant, right? That depends on hydrogen fuel, right? To power electric vehicles, and they had a sole source, right? And they neglected all kinds of other refractory energy sources that they could harvest and use, including solar, to power their cars that drove them around the plant. And so by adding, again, a few other energy producing components into the system, we were able to not only reduce their reliance on fuel that they bought, but we increased the cycling of the system and increased its resiliency. It moved from basically somewhere over here to somewhere over here. And so that created energy and reduced waste and made the system less prone to disruption. So a whole bunch of stuff that we talked about, right? And these are, but this is sort of the take-home message. This is what I want to leave you with, right? That this idea of infrastructure ecology and the use of ecological network analysis tells us the sorts of roles that we need in a well-performing system, right? How to connect that system to maximize the capacity for cycling and resilience. We can look at the impact of a particular component by taking it away, right? And that's very useful from a design perspective. And we can look particularly, because we're looking at things like cyclicity, right? Or fin cycling index, the amount of energy that's material, we can look at the nature of both the direct and the indirect connections, right? A goes to B, goes to C, goes to D, right? So A affects E. That's very hard to do. And our inability to actually do that has resulted in some really poor system design, right? Because in an ecological system, those indirect linkages are super important. Right? In industrial systems, we don't really concentrate on those because they've been difficult to analyze. right? But it turns out things that we think are really sort of competitors, right, in a sense, are actually provide mutual benefit for one another. And if we can reorganize our systems on that basis, we'll have things that work better for ourselves as well as the environment. Okay, so let me just throw this up there. These are a number of our collaborators. I've worked extensively with Dr. Brooke Grass in the Institute of Sustainable Manufacturing, and we've had a series of students. These individuals here. We've had some really excellent industrial partners that have provided access to data. We've had generous support from NSF, and we have a whole host of colleagues in China that have been really essential in helping us understand the steel mills. Okay, so I will kill my screens here now because I'm tired of looking at my own PowerPoint, and get back to you all, and I'd be happy to take any questions.
Thank you, Mark, for that presentation. Appreciate that. We're going to open it up for questions now. So if we have any questions, I see there's at least a question or two in the chat. So I'm going to open up the chat room real quick here so I can take a look at those. So we had a question in the chat box. So I'm going to bring that up again. So just so that you heard that, it's my assumption that most large corporations shy away from shifts toward carbon neutrality due to the cost. Has there been any significant economic impact on Interface due to their efforts to be carbon neutral?
You know, I don't keep the books for Interface, so that's hard for me to answer. What I can tell you is that Interface continues to be the leading carpet manufacturer in the world. And so, you know, I would imagine that if this was hurting their bottom line, they would have not continued to move in this direction as they have done, right? And you know, again, our own sort of data, and this is backed up by other things that we've done, suggests that lots of times those trade-offs are overemphasized, right? And that actually being more sustainable is a net, but you have to look at it in the right way, right? And again, the systems perspective allows you to look at it in the right way because it gives you a much more holistic perspective of the benefits, right? The costs are often easy to compute, right? The benefits tend to be less easy to compute. And so the idea that we have this negative trade-off probably has more to do with the way that we understand costs and benefits than with the actual situation itself.
Okay, thank you. We have another question here. It's great seeing how these industries are coordinating with you. What are some of the long-term goals or industries you want to apply this data to? And and how do you go about doing that?
Yeah. So the first part of that question is a little bit hard to answer. I'm actually not an engineer. So my understanding of, let's say, what would be the most effective, where the low-hanging fruit is, right, or where we can make the biggest impact is probably a lot less sophisticated than, let's say, my colleague Bert would be able to tell you. So I won't pretend that I know the answer there. I can answer the second part though, and that is that there are. So when we design infrastructure, we're typically, right, when we sort of put in sewer systems in cities, or when we let's say design some large industrial plant or some development somewhere. What the process tends to be to engage a large engineering infrastructure firm, of which there are a handful, to sort of plan this whole process out, right? To figure out what is needed, where it needs to be, what the connections are, what the buildings look like, et cetera. And so, for instance, Jacobs Engineering is one of these companies. They do really, really large infrastructure projects. They, you know, are redesigning the Ford campus in Michigan. They are doing, you know, 1,000-acre development in Chicago. They are literally designing cities in Saudi Arabia and China, right? And so they are, for lots of these kind of projects, the go-to entity. And our goal in working with Jacobs has been to sort of embed our design process into what they do so that they build those sustainability metrics and methods of analysis into their design process. And it's taken us 4 or 5 years to get to the point where we believe that they will take this up. But we are now starting to work on projects with them using this technique.
Excellent. We've got one question here in the classroom.
My question is, you showed a graph showing the urban industrial systems and how they perform better when they incorporate natural components. I was wondering why utilities have so much lower wind.
Ooh, I lost the last part of that when for a second. Say the last bit again, please.
I was wondering why utilities on that graph was so much lower with natural components than without.
Yeah, so that's a really good question. And that relates to the fundamental process that we use to generate and distribute energy, which is very open loop, right? We have a coal plant. The coal plant, the energy goes through a wire. The wire goes to your home. You use the energy to power your dishwasher, right? Your dishwasher is not 100% efficient, right? It generates all kinds of waste energy, but we don't have any way of harvesting that, right? And so our system our system is so centralized from this energy production standpoint that there's very little capacity to put a component in that moves that energy in some way back into the system, right? The only way that we can really do that effectively is to use the same methods that an ecological system uses, which is to take biomass and turn it into energy, right? Similar to what we did in the steel mill. And so one of the arguments is for decentralized energy production, right, is that it might allow us to harvest some of this waste energy that normally then just gets exported to the environment.
Thank you.
Okay, sorry, come back around just for a quick second. Thank you very much, Mark. This has been fascinating. We're unfortunately running out of time, so I'm gonna cut you off for a little bit. But thank you so much. Very, very interesting conversation. And if anybody wants to watch this video, we'll be posting it on Facebook as part of our Earth Science celebration this week. So thank you very much, Dr. Weissburg, and we wish you well. And yeah, we look forward to communicating with you more about these sorts of things. All the best.
Great. Nice to meet you all virtually, and have a good day. Be safe, everybody.
Thank you.
Cheers.